Welcome back to my channel. Hope your chemistry preparation for your class 12 CBSE board exam is going fine. So I am giving you a quick recap into the three physical chemistry chapters of solutions, electrochemistry and chemical kinetics. It's just a checklist and certain points that you tend to miss up. I'll just try to give you a very brief, quick look into the topics. So all the best for me for your exams. Let us go ahead very quickly. As I've already told you about the chapters in the previous video, these are the three chapters I'm going to deal with very quickly: electrochemistry, solutions, and chemical kinetics. And total weightage of these chapters is going to be 23 marks. Organic chemistry was 33 marks. This is 23 marks. So let us look into the topics of each chapter. First, we come to solutions chapter. Regarding solutions chapter, under solutions, the important things that I would want you to do, you should know the alloys: bronze, German silver, bronze. I have written the components. Otherwise, go through NCERT table of types of solutions. You must know under each kind what are the examples, like solid and liquid, liquid and gas. These kind of examples are very commonly asked in exams. Then learn those examples, and specifically for amalgams, you must remember amalgam, something like sodium amalgam. Mercury is the solute and sodium is the solvent, right? So because the solvent depends upon the substance which is in the same physical state as the final product. So amalgams are solids. Hence, when I say sodium amalgam, sodium and mercury, although mercury is a liquid, we will consider sodium to be the solvent. Then, if I'm asking you the solvent in air, since nitrogen is the major component of air, so solvent will be nitrogen. So this way, do all the examples that are given in the NCERT table. Regarding concentration terms, you must know the formula of sodium hypochlorite. This is given under one numerical in the description while discussing concentration terms, and there's a numerical on weight by weight percentage. So sodium hypochlorite, you should know the formula. It's a part of commercial bleaching solution, and the formula of ethylene glycol. This can be asked in any form, in the form of a multiple choice question or a numerical. So just be aware about these two options. Then one question that children generally make a mistake in: calculate mass of urea required in making 2.5 kg of 0.25 molar solution. Very commonly made mistake. This is NCERT in-text question. So what I want to bring to your notice is this is 0.25 molar solution, right? 0.25 molar. So either do it by the detailed description if you've learned it that way, or I'm explaining to you how to do it by the formula method. 0.25 molar is 2.5 kg solution, right? So if I suppose the weight of urea to be W, and W obviously I'm taking gram, upon molecular mass of urea, which I know is 60. So if I put here the value 60, this is number of moles of urea. Here I must take 2.5 kg means 2500 gram of solution. Please remember, this is the mass of solution. Very important to keep in your mind, right? So 2500 minus I have to do the mass of solute. This is going to give me mass of solvent in gram. So I'm going to multiply here with 1000. So solve it and just see. If you've done it by the unitary method, then also it's perfectly fine. But I just want to bring to your notice this point. Please remember, especially remember for molality. For molality, the most important thing is to remember in the denominator, you have weight of solvent in kg, right? And for molarity, this is one last review for you. It's volume of solution in liter. Please remember this. So we move on to the next point. One numerical: 98% sulfuric acid solution density. Calculate molality, strength, and molarity. So I am just giving you a quick look into how to solve this question. This includes almost the entire component. I'll also include mole fraction. So in general, you must know 98 gram of sulfuric acid is present in 100 gram solution. With clarity, understand everything. And when nothing is mentioned, we always assume it to be weight by weight percent. So what are we going to do? We are going to convert this to moles. This is volume mass of solution given. So what will be weight of solvent? 100 minus 9.8 is going to be weight of solvent. That's going to be 90.2. Okay, if my calculations go wrong, just check that. My purpose right now is just to help you recall the methods. So if I have to calculate chi B, that is chi sulfuric acid, what am I going to do? I'm going to take moles of sulfuric acid upon moles of sulfuric acid plus moles of water, that is solvent, which is 90.2 upon 18. Clear? This is molality. This is mole fraction of the solute. And please remember, mole fraction of the solvent could also be asked. Either do 1 minus what we calculate here, or directly chi water, you understand, is going to be 90.2 upon 18. Please read the question carefully. Upon this plus this. Read the question carefully. Your silly mistakes are to be avoided. Okay. And then if we want strength, what is strength? For strength and for molarity, we would need volume of solution. So 100 gram solution we have. How do we convert it to volume? You know, density is weight upon volume. So if you already know, you can just skip it. The ones who want a review quickly can check weight upon density. What is important here, children? Weight is 9 point. When I have to put weight upon density, weight of solution is 100 gram and density of solution is 1.2 gram per cc. Please remember per cc, which means when this cancels off, you're going to get your answer for volume in cc, that is ml. So when you substitute the values, your molarity is going to be number of moles into volume. Okay. And just remember, since this part is in cc, you have to multiply it in 1000. Now, since you are used to doing numericals mostly in gram per cc, let us suppose in exams you get it as density 1.2 gram per liter. In that case, when you're going to do the same question in the same question, children, please remember, when you're doing the same question now, instead of cc, you are going to get your answer now in liter because it's gram per liter. So you're going to get your volume in liter. So you need not mention any thousand here. Be extra careful. If they give you an applied question, you're used to doing it this way, they might ask you this way. This one point is to be kept in mind. And when it comes to strength, strength is nothing but molarity by molecular weight. Or in other words, I can say, if you are asked to calculate strength, you can simply put 9.8 upon 98. This is the, this is strength is going to be 9.8 upon, this is 100 into 1.2. This is volume in cc, this is weight, and here 1000. Okay, this is going to give you the strength of solution. So I hope this is one question which covers everything about concentration terms. Then next important question is, what is the effect of temperature on concentration terms? Just remember, temperature affects only those concentration terms which have volume in them. For example, strength, whose unit is gram per liter, will be affected by temperature. Molarity will be affected, and not affected will be the concentration terms like molality or mole fraction, because these have no volume term. Only volume gets affected by temperature, mass is not. Then which concentration terms will a chemist use when working with variable temperature? Since molarity changes with temperature, so a chemist will prefer to use small m, molality. Which concentration terms are dimensionless? The ones which have same units in numerator and denominator. For example, mole fraction. Mole fraction is a dimensionless unit. It doesn't have units. Okay, dimensionless term. So next we come to solubility. The important questions about solubility, Henry's law. Remember, Henry's law determines ideal solutions of gases in liquids. Okay, solutions for gas and liquid which obey Henry's law at various concentrations are considered ideal solutions. Two formulas are given in NCERT. What you have to be careful about, if this formula is used, the unit of K is going to be obviously kg per bar. And if I supposing give you that a particular gas has K 10 kg per bar, this is only if they choose to give you an applied question, a difficult question. And K2 for another gas is 5 kg per bar. And if I ask you which is more soluble, you understand solubility of this is directly proportional to K. So this is going to be more soluble gas. Okay, this is if they ask applied. Now, if this formula, there's a second formula given in your book, P is equal to KH chi. In this case, solubility. Solubility is basically expressed in terms of This P solubility, is expressed in terms of either in this formula by M and in this formula by chi. And solubility is inversely proportional to chi. This is KH. Here it is inversely proportional to KH. In this case, it is directly proportional to KH. Supposing I give you that KH1 for a gas is 10 bar and KH2 for another gas is 5 bar. This time, which gas is more soluble? This one is more soluble. Why? Because this Henry's law constant is inversely proportional to solubility. And in case nothing is mentioned, if they simply tell you the Henry's law constant, they just use this term, no units, nothing. Henry's law constant of gas A is greater than gas B, then which is more soluble? You will say this is more soluble. Why? Because we, by convention, unspoken, we assume this formula and we assume that solubility is inversely proportional to KH. And then there's a conceptual about this fishes. Why fishes are more comfortable in cold water than in warm water? Why? Because of the solubility variation. Just do that. So then do the numerical on Henry's law, do the in-text NCERT back exercise numerical, or if they ask you an applied question, they can ask you something like this, where we need to use M is directly proportional to P, or M1 upon M2 is P1 upon P2. For example, if I tell you at 2 bar pressure, the solubility of something is 2 kg, then what will be its solubility at 4 bar? Right? So that means I'm given M1, I'm given P1, I'm given P2, and I'm asked M2. These kind of numericals can be asked on Henry's law. This is just a last moment checklist. Conceptuals, effect of temperature and pressure on solubility of carbon dioxide or any gas in water. And you know that since the dissolution process of gas in liquid is exothermic, so dissolution of a gas decreases with increase in temperature. Less gas is dissolved with increase in temperature, and it increases with increase in pressure. Then revise bends and anoxia. These can be direct questions asked from your NCERT. Vapor pressure questions, Raoult's law. Now, one major mistake that children have been making while we check in the school exams, we check papers. Raoult's law is categorized into two different categories. One is mixture of two miscible volatile liquids, volatile components. Here, when both the liquids are volatile, so total pressure is given by P1 naught chi A plus P2 naught chi 2, where chi 1 and chi 2 is the mole fraction. These are the mole fraction of the components 1 and 2, both of which are volatile, and these are the vapor pressures of the pure volatile components. Total pressure is given by this. Okay, and then do the graph and the in-text numerical given at the end. That will give you a practice. Do that question with understanding. I hope you've already done. So I'm just giving you a quick overview of the kind of numericals for understanding. This is a liquid mixture. This is the liquid phase. In liquid phase, Raoult's law is applicable. That means PA is equal to PA naught into chi A. This is applicable in liquid phase. In vapor phase, this is the vapor phase. In vapor phase, the formula that is applicable is PA is going to be chi A dash into P total. Where what is PA naught? This is the vapor pressure of pure solvent A. Okay, and this is mole fraction of A in liquid phase. This is mole fraction of A in vapor phase, and this is the total pressure. As an example, if I tell you chi A is 0.2, chi B is 0.8 in the liquid phase, and PA naught and PB naught are given, then what is PA in, according to, if I want to relate the pressure contribution of A to the mole fraction in the liquid phase, I'm going to use this formula. I'm going to get this. If I want to compare it to PB, that is the contribution of component B to the total pressure, PB is PB naught into chi B. What is chi B? Chi B is the mole fraction of B in liquid phase. Okay, so I'll get total pressure as 1.8. Now, supposing I want to compare this with chi A dash or find out chi A dash. How am I going to calculate chi A dash? Chi A dash is going to be equal to PA upon P total. What is PA? PA is this 0.2 bar and P total is this 1.8. So when I take a ratio of this, I'm going to get chi A dash. What is chi A dash? It is the mole fraction of component A in vapor phase. Okay, this is the gist of all the kinds of numericals that can be asked. And then there's one line given at the end of a numerical in your book. At equilibrium, vapor phase is richer in more volatile component. More volatile component means whose P naught is higher. So just keep these points in mind. Then Rawls law is a special case of Henry's law. Do this as such as given in NCERT. Rawls law. Next topic is Rawls law for a solution of a non-volatile solute to a volatile solvent. Like in the previous example, two volatile mixtures means you have two liquids. Like let us say you have benzene plus alcohol. That is two volatile liquids mixed together. The one I've just talked of, that formula will be applicable. That is P total is equal to PA naught chi A plus PB naught chi B. But in case I give you an example where I ask you, I have water plus urea. Urea is a solid, non-volatile. So now the formula that's going to be applicable is going to be PS, vapor pressure of the solution, is going to be equal to P naught, where P naught is vapor pressure of solvent, in this example, water. And chi A is also mole fraction of solvent, that is water, because the solute is non-volatile. It is not contributing to total vapor pressure. So be clear when one of the questions that is generally asked is define Rawls law. So just be careful about reading. They've asked you for what, which particular situation. Okay. The next important question is ideal and non-ideal solutions. Ideal solutions obey Rawls law at all concentrations. Please be careful about mentioning this. Sometimes half a mark is deducted if this is not written. Obeys Rawls law at all concentrations. Ideal solutions. Which solutions? Liquid in liquid solutions. Which obey Rawls law at all concentrations are considered ideal. These are the components you must include. Intermolecular forces of both the components should be same. Learn the NCERT examples. This is the graph. For graph, please be extra careful about plotting these points. Okay, very important. And supposing if I ask you on this graph, if I ask you graphical question, what is this point? You know this point is going to be PB naught. Why? Because here chi B is 1. That means here I have pure solvent 1, where this corresponds to vapor pressure of pure solvent and this corresponds to vapor pressure of A, PA naught. So if I ask you which out of the two is more volatile, since PA naught is higher, it is the more volatile component. All the probable questions as MCQs or as write a note. Then positive deviations, new force is weaker. Both these are positive. This is positive means the mixing process is endothermic. That means temperature decreases on mixing. This can be asked directly, indirectly, write a note or multiple choice. Very high yield topic, children. Often asked. Delta V mixing positive, new volume is more. Examples in NCERT, new vapor pressure is more. And P is not equal to P naught chi. That means, what does this mean? This means Rawls law is not obeyed. Not obeyed. Deviations means those solutions which do not obey Rawls law. And this is the graph. The dotted line gives the ideality. Must label the graphs. And this shows that the observed vapor pressure is more than what is expected from Rawls law. And why is it so? Because the new forces are weaker. And exactly on the same lines, you're going to think of negative deviations, similar concepts under negative deviations. Then we have azeotropes. With examples, learn maximum boiling azeotrope, minimum boiling azeotrope. The gist is maximum boiling azeotropes are formed by all those mixtures which have negative deviations, and minimum boiling with positive deviations. Learn examples in NCERT. You can be asked to identify or write a note or define. And children, in case you are asked to define or write a note, it's mandatory that you mention one or two examples with your answer, even if not asked. Colligative properties, those which depend on number of particles or concentration, okay, and not on nature. What is the importance of studying the colligative properties? To determine molecular weight, and each colligative property is inversely proportional to molecular weight. This is one point you have to keep in mind. For non-electrolytes like urea, glucose, non-electrolytes means which are not going to undergo any change in solution, neither associate nor dissociate. The first colligative property is relative lowering of vapor pressure, derived from Rawls law. it goes as this: P naught minus Ps upon P naught is chi B, where P naught is vapor pressure of the pure solvent. This is of the solution, and this is also solvent. Chi B is mole fraction of solute. Please remember with clarity, Ps is equal to P naught into chi A. This is for a solution of a volatile liquid with a non-volatile solute. Okay, this is Ps, vapor pressure of solution, is directly proportional to mole fraction of solvent. But relative lowering of vapor pressure is equal to mole fraction of solute. And if from here I ask you lowering of vapor pressure, then the formula becomes this. And this is a constant term. Hence, P naught minus Ps is directly proportional to chi B. I repeat, Ps is directly proportional to chi A. P naught minus Ps upon P naught is equal to chi B, and P naught minus Ps is directly proportional to chi B. Please keep these three components in your memory. Okay, and for dilute solutions which are less than 5% concentrated, the formula applied can be P naught minus Ps upon P naught is equal to Nb upon Na. Otherwise, the formula for every solution is this. And don't use in boards this formula. Please avoid using this formula for boards. This is only for JEE. Don't use it for boards. Okay. Then these are the main points I have written. Just read them through. I've just explained to you. Clear? So very important point for you to understand: P naught is an absolute quantity vapor pressure of a pure solvent. This depends only on nature. This doesn't depend upon number. Ps is vapor pressure of solution. This will also depend upon nature. But P naught minus Ps upon P naught, which is relative lowering. Relative lowering means lowering with respect to original. This is independent of nature, but depends only on the number. Number of what? Number of particles of the solute added. Doesn't depend upon the nature of solute, which means if I add 5 moles of glucose or 5 moles of urea, the lowering will be same, other components remaining the same, such as solvent. Elevation in boiling point. What are the important points? Delta TB is kbm. This is again the formula to be applied for non-electrolytes like urea, glucose. What is kb? Molar elevation constant or ebullioscopic constant. Please remember its definition, which says it's the elevation in boiling point for a 1 molar solution. Okay, remember its units. TB minus TB naught goes by this formula. This is weight of solute, molecular weight of solute, weight of solvent, remember in gram and into 1000. TB naught is the boiling point of pure solvent. It depends on nature. Obviously, boiling point of water will be different than benzene, than alcohol, etc. Kb is also a property of solvent. It depends on nature of solvent. TB minus T naught, that is the elevation, depends on number. Why elevation? Because understand TB is always greater than TB naught. So we get an elevation. These are the important points to be kept in mind. Now, this is a very, very common mistake children make in spite of repeatedly telling. If they ask you graphically, this is also a previous year question, graphically express elevation in boiling point and depression in freezing point. Please draw this graph with clarity. This axis vapor pressure, temperature. This is showing the solvent vapor pressure curve. This is showing solution. If they ask you anything applied, you understand with temperature, vapor pressure increases, right? So this graph is going upwards. This is also going upwards for the same reason. But why the solution curve is below the solvent? Because we are talking of solutions having a non-volatile solute in a volatile solvent. Okay. And hence this graph is below. Now, what are we going to do? Boiling point is the temperature at which vapor pressure of any component becomes equal to external atmospheric pressure or any external pressure, chosen pressure. Okay, so I'm talking about here standard boiling point. This point, 1 atmosphere is the external pressure. So the temperature at which the vapor pressure is going to match with external is going to be called as boiling point of the pure solvent, because I'm talking about this on the pure solvent axis. And when I extend this to meet the solution curve, this is going to be the boiling point of solution. So we can also observe there's an elevation in boiling point. Please learn this nicely. When you're asked about depression and freezing point, again the same two lines, but this time the definition is different. What is the definition of freezing point? It's a temperature where the vapor pressure of solvent matches with the frozen, the solid solvent. So this is the graph curve for frozen solvent. So the point where the two meet, this is TF naught, and where the solution curve meets with the frozen solvent is TF. And you can observe with clarity TF is less than TF naught. Please remember this. Revise, last moment revision. Don't just make any two lines and join any two things anywhere. Be very clear about this. Cram it well. Depression and freezing point goes similarly as we've talked about elevation, molar cryoscopic constant or molar depression constant, definition, and everything else goes the same. And then these formulas, you must know Kb, which is a property of the solvent, right? So it depends on molecular mass of the solvent. This is boiling point, and the temperature, the value should be put in Kelvin. R, the unit has to be 8.314 joule per Kelvin per mole, delta H vaporization in joule per mole. Okay, the unit of R has to be similar to the units in which you're taking this. So for water, TB is 373 Kelvin. Now, KB in terms of latent heat of vaporization goes like this, where latent heat of vaporization is nothing but enthalpy of vaporization upon molecular mass. Enthalpy of vaporization is defined per mole. Latent heat of vaporization is defined per gram. Okay. And similar concept for freezing point. You can just pause and just read it through again. Osmosis and osmotic pressure, the last colligative property, pi is equal to n by v RT. CRT, what is important? You know these. For n is WB upon MB, this is V, and this is RT. What is important here is to remember the units. If you want the answer for pi in bar, this is 0.083 R liter bar per mole per Kelvin. Volume in liter. Please remember, not in cc, in liter. Why? Because of the unit of R. Here V has to be in liter and pi will come out to be in bar. Please be extra careful about the units being used. Conceptuals on osmotic pressure. Advantage of this method over other colligative properties, like this works at normal temperature, and proteins, biomolecules, etc. do not denature. Those points revise once again. What are the examples of natural and synthetic semi-permeable membranes? Go through that. And then which semi-permeable membrane we use in reverse osmosis, that also you must do. And for isotonic solutions, isotonic for non-electrolytes means pi 1 is equal to pi 2. So pi is equal to CRT at the same temperature for the same osmotic pressure. What are we left with? C1 should be equal to C2 for isotonic. And C1 means N upon V. If the volume is same, then N1 is equal to N2, which means this formula. So out of these four, generally, three components are given. Let us say I tell you a 5% solution of cane sugar, right, is isotonic with a 10% solution of X. Find out X, a very, very popular form of question. What are you going to do? You're simply going to put here 5 upon 342. That is weight of solute upon molecular weight, right, is equal to 10 upon molecular weight of X. Just solve it and you get the answer. This type is very important. Then for electrolytes, Van 't Hoff factor, pi is equal to ICRT. For isotonic solutions, it will be I1 pi 1 is equal to I2 pi 2. Okay, for example, if I tell you a 5% solution of cane sugar, this time if I tell you is isotonic with a 10% solution of AB, which dissociates to give A plus and B minus. And let us say I mention it completely dissociates. What are you going to put now? This time I1 is going to be 1 because cane sugar is a non-electrolyte. This is 5. This is 342. Okay, because our formula is going to finally become I1 C1 is equal to I2 C2 because RT will be constants. And similarly from here we are going to get I1 N1 upon V1 is equal to I2 N2 upon V2. This is also same because we are talking about percentage. So what are we left with? We're left with number of moles comparison. I for a non-electrolyte is 1. Number of moles means 5 upon 342 for cane sugar. This is going to be 2 because they have told us this electrolyte dissociates to give this and completely dissociates. So I know I2 is equal to N. But in case they had stated it undergoes 80% dissociation, then we would have used the formula I is equal to 1 minus alpha plus N alpha and proceeded. Okay. So I'm talking about complete dissociation. So I'll take this as 2. I'll take this as 10. And this is molecular mass of AB. So you're going to solve this to get molecular mass of AB. I hope it's clear. So this is just for your last moment review. Applications of osmosis go through from the last page, the last paragraph after this topic given in NCERT. There are many applications like why pickles are preserved with high salt, jams with high sugar, all those just go through. Reverse osmosis, example, what is reverse osmosis and desalination and the semi-permeable membrane which is used because reverse osmosis requires high pressure. So we have a special semi-permeable membrane, just recall that. Desalination of seawater is the example and application is RO systems. Then abnormal molecular mass is the last topic. Van 't Hoff factor. I is equal to observed colligative property upon calculated colligative property. I is calculated molecular mass upon observed molecular mass. Observed means experimental also. Calculated means theoretical also. And why these two formulas? Because every colligative property is inversely proportional to molecular weight. Okay. So I for non-electrolytes is 1. For electrolytes, for non-electrolytes, we know I is 1, right? For electrolytes, dissociation I is greater than 1. Dissociation I, the dissociation formula that you can remember, or if you've remembered it in any other way, it's fine. I is equal to 1 minus alpha plus N alpha, where N is the number of particles on dissociation. For example, if you have 80% sodium chloride solution, then alpha is going to be 0.8. Alpha is 80 upon 100. N will be 2. Why? Because sodium chloride ionizes to give sodium ion and chloride ion. I is 1 minus alpha, that's 0.8. 2 is N into this, answer comes out to be 0.8. If it was potassium sulfate, then N would have been 3 and so on. Okay, this is for dissociation. And then for association, acetic acid and benzene, I is less than 1. For every association, I is less than 1 because acetic acid and benzene dimerizes. Dimerizes means 2 units start behaving like a single molecule. The formula goes like this. Again, an example, 80% acetic acid dimerizes in benzene. So I is equal to 1 minus 0.8 plus 0.8 by 2. That is equal to 0.6. Okay. So most of the questions are based on this. Now, various colligative properties for electrolytes will get modified using the I factor with these formulas. Clear? Remember? And also remember, I is going to be equal to 1 minus alpha plus N alpha if it's dissociation, or if it's association, 1 minus alpha plus alpha by N, as we have already discussed in each case. Okay. So next is for complete association or dissociation, I is always equal to N. That means if I tell you sodium chloride is 100% dissociated, then that means N is 2. So I is going to be equal to 2. How? I have shown you the substitution and the example. Table just before the last numerical, children, just before the last numerical of osmotic pressure and Van 't Hoff factor, there's one table given. So the conclusion of that table can be asked in the form of a multiple choice question if they choose to give you some indirect questions. So what is the gist of that table? With increase in dilution, you'll see there's 0.1 molar, then 0.01 molar and 0.001 molar, 3 columns made, right? With increase in dilution or decrease in concentration. This is increase in dilution or decrease in concentration. You will observe I increases. And at infinite dilution, the last column you will observe I is equal to N. So just observe this. Okay. So practice the last numerical with understanding that make you solve any applied numerical that comes. I hope this helps, children. So this was about solutions. You can give one quick on double speed, a quick revision. The things you know, good. The things you don't, go through it. All the best. God bless you.